Bismillahirrahmanirrahim. Assalamu alaikum everyone. So this lecture is about interrupts, and the microcontroller that we are discussing is PIC18F452. So we'll just proceed without wasting any time. So the sources of the sources of interrupts in PIC18F452 are timers, pins RB0, RB1 and RB2, because these have been dedicated for the external hardware interrupts End0, End1 and End2. Port B change interrupts, so you can see that there are 4 pins RB4, RB5, RB6 and RB7 that are dedicated for a change detection interrupt. So whenever there's a voltage difference that occurs on port B, an interrupt would be generated in the PIC18F452 if you have enabled the very specific interrupt enable bit for that port B change interrupt. So these things we'll discuss it in the coming section, but keep this thing in your mind that whatever module, if it has a flag, then it is able to generate interrupts in PIC18F452. So you can see that timers have flags, external interrupts. You have never seen flag for this one because this is an external hardware interrupt, N0, N1 and N2. Then you have serial communication USART interrupts. You remember receival flag, transmittal flag. So whenever something is received, there is RCIF flag, it's raised, and whenever you transmit something, the TXIF flag, it's raised. So whatever module, if it has a flag, it can be used to generate interrupt. Then is ADC, you remember analog to digital converter, ADIF, it can be used to generate an interrupt. Then we have CCP module in our PIC18F452, compare, capture and pulse width modulation, where we have CCP-IF flag. So all of these are the sources of interrupts that we need to remember because we can use them in our code. So what's the basic need that we have to generate interrupts? Normally when we were using flag polling, so what's flag polling? Flag polling is something that you make your code stay at some point. So if I talk about timers, you specifically remember that if we were generating a frequency or something related to timers, we used normally the while command that stopped the code from further proceeding until and unless the flag is raised, until and unless the flag has shown the signal that the timer has completed timing. So in that process, our timers do stop the code from further running because our pointer has stopped on that very while command where we are waiting for the flag to be raised. So in order to escape from this waiting time that can hinder our further prospects of the code or the further lines to be from execution, so what we do is that we use interrupts. So interrupts are like something that they do not make us wait anywhere in the code. Instead, they help us to move the pointer from one side, from the main code, and take it to the pretty small interrupt code where we have generated something related to that flag, and then come back to the main code. I'll explain this with the help of an example. So you just need to study it till the moment, and we'll discuss it in the detail in some examples. So these are the sources of interrupts that are in front of you. Then there are registers related to interrupts. There are 10 registers which are used to control interrupt operation. These are Endcon, Endcon 2, Endcon 3, PIR1, PIR2, PIE1, PIE2, IPR1, IPR2, and all of these registers you need to remember that they are 8-bit registers. So what do these registers contain? These registers contain 3 kind of bits. One is the interrupt flag, which I've already told you, like for timers we have, for timer 0, TMR0IF, timer 0 flag. For ADC we have ADIF. For CCP we have CCPIF. So these registers contain the interrupt flags. Then we have interrupt enable bits, i.e. ADIE, CCPIE, and similarly all those modules which have flags as I have already told you that they are able to generate interrupts. So all of them would have interrupt enable bits, which controls the interrupt generation. If an interrupt enable bit is turned on, the turning on of interrupt enable bit will let your flag raise an interrupt. And if you have interrupt enable bit turned off or interrupt enable bit turned to 0, that would not allow your flag to generate any interrupt in the system. So that's the very important point of interrupts, that whenever you are using interrupts and you have used any flag, any module as a source of interrupt, but you have mistakenly or deliberately just forgot to turn on the interrupt enable bit for that specific module, then what will happen is that your flag, even if it's raised, it won't generate an interrupt until and unless you enable that IE bit, interrupt enable bit of that particular module. So we'll just move forward. As I've already told you that each interrupt source has 3 bits to control its operation: a flag bit, an interrupt enable bit, and a priority bit. So a flag bit indicates whether an interrupt event has occurred or no. An interrupt enable bit is just used as a switch which enables or disables the interrupt source. Then is the priority bit. What does this bit do? So this priority bit is something that's related to another master switch, which we call as IPEN, interrupt priority enable. So we'll discuss this thing in a bit more detail, that what is a priority bit and how is this being controlled by the IPEN, interrupt priority enable bit. So we'll discuss this in detail. For example, we have a timer 0 over here, and the flag bit for timer 0 is TMR0IF. The interrupt enable bit is the TMR0IE in the Endcon register, and the priority bit is the TMR0IP, which is present in the Endcon 2 register. So these two registers that are in front of you, Endcon and Endcon 2, these were listed in the last slide where we have discussed some 10 registers. All of them were 8-bit. So all of these registers contain either of these interrupt flag and interrupt enable and priority bits. So what's the main thing that you have to remember is that what do these bits do? You'll have the data sheets in front of you, but you need to know that how do you use them. So we'll just move forward towards the registers. So we'll discuss only this Endcon register and 2 more registers in detail. You can see that this Endcon register, the very first 2 bits, GIE and PEIE, these have 2 names more. GIE has one name, GIEH, and PEIE has the other name, GIEL. So what's the difference and why do these bits have 2 names? And there's no bar on one of them, so that means that that's not an alternative name, that's a different name. So I was telling you about the IPEN bit, interrupt priority enable bit. So before discussing these 2 bits in detail, I'll just move you to the IPEN bit, and then we'll come back to that point. Yes. So the Endcon register has bit number 7 as IPEN. IPEN is the interrupt priority enable bit. So you need to listen to this very carefully. If this bit is 1, then the microcontroller will look that what module has a high priority for interrupt generation and which module has a low priority for interrupt generation. But if this IPEN, interrupt priority enable bit, has been turned to 0, then your microcontroller would not look at the priority levels of any of the modules. It will generate the interrupts accordingly at the same level, without any biasness, without any discrimination on the basis of high priority or the low priority. So if IPEN is equal to 1, this enables the priority levels, and if IPEN is 0, this disables the priority levels and treats them equally whether you have turned the interrupt priority for that specific module to be high or to be low. It would not look at their priority levels if the IPEN is equal to 0. So that's why I was mentioning IPEN is equal to as the master switch for the interrupt priority bit. We'll move back to the Endcon register. So yes, we have GIE and GIEH pin in front of us. So you can see that if IPEN is equal to 0, then this bit would be read as GIE, and turning this one on would enable all the unmasked interrupts. Unmasked interrupts, by unmasked interrupts we mean that the interrupts for which interrupt enable has been turned on. And if this bit is turned 0, then this disables all the interrupts. But if IPEN is equal to 1, then this bit is read as GIEH, global interrupt enable for the high priority bits. So this, if turned 1, if IPEN is equal to 1, will enable all the high priority interrupts, and if it's turned 0, then it's something that I'll not play and I'll not let anyone play. It will disable all the interrupts. So we have a similar case with the PEIE, peripheral interrupt enable bit, if the IPEN bit is 0. So what this pin would be read as then is PEIE for the IPEN is equal to 0 case. And if it's turned on, it will enable all the unmasked peripheral interrupts. So the hardware interrupts are not included over here. And if it's turned 0, then this disables all the peripheral interrupts. But if IPEN is equal to 1, that means this bit would be read as GIEL, or I can say that global interrupt enable for the low priority bits. And if it's turned on, if it's 1 in the case where IPEN is equal to 1, then it enables all the low priority peripheral interrupts. And if it's turned 0, in the case IPEN is equal to 1, then this disables all the low priority peripheral interrupts. So this is very important, that these two bits, their function depends on if IPEN is equal to 0 or IPEN is equal to 1. The rest you can see easily, that I'll just consider the case of this timer 0 and end 0 IE. That timer 0 IE is the timer overflow interrupt enable bit for the timer 0, and it enables the timer 0 flag interrupt for if this bit is turned 1. That means that if you have turned this bit to be 1, then it will generate the interrupt if the timer 0 flag is raised. And if this TMR 0 IE is 0, then even if timer 0 IF is raised, the timer 0 flag has been raised, it would not enable the interrupt bit, it would not enable the interrupt generation. So similarly, you have interrupt enable bit for end 0, for port B change interrupts, and there we have TMR 0 IF, that's the flag bit for timer 0, that's the flag bit for end 0, and that's the flag bit for the RB pins where the change interrupt module is considered. So moving forward, as I've told you, these are all the normal bits that we have over here in these registers, that are the interrupt enable, interrupt flag, and the priority bits. You can see these 3 bits in front of you: int h0, int h1, and int h2. These are only the option, this is only the option that's available in the external hardware interrupts int 0, int 1, and int 2, where we have the option that if we want to trigger the interrupt on rising edge or the falling edge. So you can see that all of the rest of the inputs, rest of the interrupts, they were the software based interrupts that were being raised or generated when the flag was raised. So these flags for the int 0, int 1, and int 2, these are raised when an external input is given to the microcontroller at RB0, RB1, or RB2 pins for int h0, int 0, int 1, and int 2 respectively. So there we have an option that if we select this bit int h0 equal to 0, then this will, and in parallel we have enabled the interrupt enable bit for this flag for int 0, that is int 0 IE, which we had seen in the Endcon register. I can show you again int 0 IE, this bit over here, int 0 IE, you can see. So this int 0 IE, if it's turned on, if it's turned 1, then what we'll have this int edge 0 to be selected, and int edge 0, if it's selected to be 1, then it will generate an interrupt on the rising edge, and if it's selected on 0, then it will generate an interrupt if there occurs a falling edge on the external pin int 0 RP0. Same is the case for int edge 1, int edge 2 for the int 1 and int 2 interrupts. And then these bits are very easy to understand. I don't think we should waste time over here. So one thing you should remember, that there's no priority bit for external int 0. That means it's always at high priority. And for the other pins, you can see int 2 IP, int 1 IP. Here you can see that you can set it at high priority or low priority. And if you have set it at low priority, you have int 2 IP is equal to 0, and your IPEN is also equal to 0, then that makes no difference if you make int 2 IP is equal to 1 or int 2 IP is equal to 0. But if IPEN, interrupt priority enable bit, is turned on, it's equal to 1, then int 2 IP, if it's turned 1, then your interrupt module will give a high priority to int 2 and a low priority to int 2 if it's turned int 2 IP is turned 0. So here's a graph that will explain everything in front of you. So let's start from the beginning. How to use interrupts for specific peripheral, let's discuss it. First of all, the thing that you need to change is the IPEN bit. If IPEN bit, interrupt priority enable bit, is 0, then it will treat the whole system as a default uni-level interrupt system. There would be no high priorities, there would be no low priorities, and even if they are set at low or high priority, they would not be considered. But if IPEN is equal to 1, then you have two-level interrupt system. One is the high level interrupt system, high priority level, and other is the low priority level. So let's go back to the default uni-level interrupt system. The very first thing that you need to do is that you have to enable the interrupt enable bit of that very specific module that you are using to generate the interrupt. For example, if you're using timer 0 interrupt, you will use TMR 0 IE as the interrupt enable bit. Then you will set the GIE bit. You can see we haven't written GIE/GIEL bit. Why? Because we have turned IPEN is equal to 0. So we have unilevel interrupt system over here, and we only need to set the GIE bit. We are not naming it as GIEL bit. And the third thing that you need to do is you have to set the PIE bit, which is the peripheral enable input interrupt enable bit. So again, we are not naming this one as GIEH bit because we know IPEN is equal to 0. And once you have set these three bits, you are ready to generate the interrupt with the help of your specific module if you're using timer 0, int 0, or any other module. Now is the case when IPEN is equal to 1. If IPEN is equal to 1, then what you need to do is that you need to set the interrupt enable bit. For example, if we are considering the timer 0, we have TMR 0 IE. Now you set the GIEH bit. Remember, it's the same bit which is called as GIE, but if IPEN is equal to 1, that bit changes its name, its function, and now it controls the high priority modules for interrupt generations. And then you set the priority bit. You know, you are not changing the PEIE bit over here. Why? Because in the case where IPEN is equal to 1, this bit is not anymore the PEIE bit. It's now the GIEL, global interrupt enable for the low priority bits. So you set the priority bit over here, and for the module that you select the priority. If you want it to run at high priority, and if you have turned the GIEH on and the interrupt enable for that bit, you will set its priority to be high. So if we are considering the timer 0 module, TMR0 IP would be equal to 1. And if we are considering the low priority system where IPN is equal to 1, then for that one you will need to set the interrupt enable bit of that particular module is equal to 1. Then you'll set GIEH and GIEL both. If GIEH is equal to 0, this bit over here it's set to 0, then this disables all the interrupts, not mentioning higher ones or lower ones, all without any discrimination. And then if you turn this GIEL bit off, this will turn off all the low priority inputs, not the high priority ones. They will still remain on. So now if you want to run a priority interrupt module on low priority, so what you'll do is that you'll set the enable bit of that interrupt module, GIEH bit is equal to 1, GIEL underscore bit is equal to 1, and then that priority, then that module will have a 0 priority bit. So if we are considering the TMR0, the TMR0 IE is equal to 1, GIEH is equal to 1, GIEL is equal to 1, and TMR0 IP is equal to 0. We'll set it at low priority for the 2-level interrupt generation system. This thing is again explained over here. If IPEN is set, then 2-level interrupt priority system is used. If IPEN is cleared, then a default unilevel interrupt system is used. So that's again the same thing that we are repeating over here. 3 bits in order to for you can see an example enable the ADC interrupt, GIE bit, PEI bit, and ADI bit for enabling interrupt of the ADC at high priority without using IPEN. So that means we are using IPEN is equal to 0 over here. And with priority enabled, what we'll do is GIE, GIH, PEIE is used as GIEL, and to make any peripheral work with high priority we have to set the GIEH enable bit, priority bit, and low priorities we have to set the GIEL, GIEH both, and enable bit of the associated peripheral. Here we will have the priority bit as 1, and here we will have the priority bit as 0. So this is the routine that you'll follow in micro C. That's the last slide that we are going to discuss in this video, and I'll discuss an example in the next video because this is already getting longer than we had expected. So void interrupt, this function will include the high priority interrupts, and this function over here would include the low priority interrupts. So if you have turned the GIEL is equal to 0, this function would never be called. Void interrupt underscore low would never be called, this function over here. While if you have turned the GIEL is equal to 1 and you have IPEN is equal to 1 as well, then this function would be called automatically whenever any low interrupt module generates a flag. Low priority interrupt module generates a flag. This function and this function will have the fixed names in PIC18F452. You cannot change their names, but you can change the content that you have to write over here. So we'll consider the examples in next video. So I hope that this thing is now clear to you. Still, if you have any questions or any comments, you can mention it in the comment section. Thank you. Take care. Allah Hafiz.